In July 1969, three men embarked on a journey that would forever change humanity. But the images you're about to see are not the official NASA footage. They have been meticulously recreated to reveal the secrets behind humanity's greatest engineering achievement, secrets that remained hidden for decades. What you thought you knew about Apollo 11 is just the tip of the iceberg. Welcome to the true story of how we built the machine that conquered the moon. Imagine a structure 111 meters tall, taller than the Statue of Liberty, weighing 2,970 tons, the equivalent of 400 stacked elephants. This was the Saturn V, and its construction revealed challenges that defied all known laws of physics. But here's the first secret. When NASA approved the construction of the C5 project in January 1962, the engineers had no idea how to make it work. The first stage, built by Boeing, needed to generate 7.5 million pounds of thrust, a force so devastating it could destroy the launch platform itself. To put this magnitude into perspective, this power equals 85 Hoover dams operating simultaneously. The solution? 5 F1 engines, each the size of a small house. But here's what few know. These engines were originally designed in the 1950s, a full decade before Apollo even existed. Rocketdyne engineers envisioned the largest engine possible that might be needed in the next decade, without knowing they were creating the key to the moon. While the world admired the raw power of the Saturn V, the true engineering miracle was hidden in what they called the instrument unit, a circular section just 3 meters tall, positioned above the third stage. This was literally the brain of the rocket. Inside this capsule, hundreds of computers, primitive by today's standards, but revolutionary for 1969, calculated real-time trajectories, adjusted course, and made millions of decisions per second. What makes this even more impressive? This entire navigation system had less computational power than the smartphone in your pocket today. And yet, it was capable of calculating with millimetric precision the 384,400-kilometer trajectory to the moon. But perhaps Apollo 11's greatest engineering secret was the lunar module, a spacecraft that looked like it was assembled with aluminum foil and duct tape. And to some extent, it was. Grumman Aircraft received one of the most impossible contracts in history. Create a spacecraft capable of landing on the moon and then taking off again, but weighing less than a small car. The solution was so radical it defied all traditional aeronautical concepts. The lunar module's walls were only 0.012 inches thick, thinner than domestic aluminum foil. On Earth, you could puncture this structure with a screwdriver, but in the vacuum of space, it became one of the most resilient structures ever created. The secret? Engineers realized that in space, the aerodynamic forces that act on Earth don't exist. There was no need to resist wind, rain, or atmospheric pressure. Only the deadly vacuum of space. Here we arrive at what may be Apollo 11's best-kept secret, the command module's heat shield. This was the only part of the spacecraft that would return to Earth, and the only barrier between the astronauts and certain death. When the command module re-entered Earth's atmosphere at 40,000 kilometers per hour, its surface would reach temperatures of 2,760 degrees Celsius, hotter than molten lava. 1 degree beyond calculations, and the astronauts would become vapor. NASA developed a material called Avicoat, a phenolic resin in honeycomb form that literally burned in a controlled manner during re-entry. Each hexagon was filled by hand, one by one, by technicians using special brushes. There were more than 300,000 individual cells. Artisanal work in the space age. While Neil Armstrong walked on the lunar surface, his words traveled 384,400 kilometers through the vacuum of space until they reached your ears. But how? Apollo 11's communications system, developed by General Dynamics, was a masterpiece of engineering. A high-power antenna on the command module, actually an array of 4 31-inch reflectors surrounding an 11-inch square reflector, maintained constant contact with Earth. But here's the detail few know. During launch, this antenna remained folded parallel to the rocket. Only later, in space, it unfolded like a mechanical flower, automatically orienting itself toward Earth. The signal was so weak when it reached Earth that it needed to be amplified trillions of times, a whisper crossing the universe. To truly understand the magnitude of Apollo 11, we need to talk numbers. 41 separate engines controlled different aspects of the mission. The rocket consumed 15 tons of fuel per second during the first stages. Only 3.8% of the initial mass would reach Earth orbit, and less than 1% would return to Earth. It was literally a machine designed to destroy itself in a controlled manner, leaving only a small capsule to tell the story. But behind all this revolutionary technology was something even more impressive. 500,000 people working toward a single goal. Engineers, technicians, mathematicians, welders, programmers. A workforce larger than many armies. And here's perhaps the most surprising secret of all. Many of the technologies that made Apollo 11 possible were invented specifically for this mission and then adapted for civilian use. Microchips, advanced composite materials, computer navigation systems. Technologies we consider common today were born from the impossible necessity of reaching the moon. When Apollo 11's command module splashed down in the Pacific Ocean on July 24, 1969, it carried more than 3 astronauts and lunar samples. It carried the DNA of humanity's new era. The same engineering principles that took Armstrong, Aldrin, and Collins to the moon are present today in everything from the GPS on your phone to modern aircraft materials. Apollo 11 wasn't just a space mission. It was a technological catalyst that continues shaping our world 5 decades later. The scenes you've seen were recreated because they show something the cameras of that era couldn't capture: the true magnitude of human effort behind Apollo 11. It wasn't just about reaching the moon. It was about pushing the limits of what human engineering could achieve. In 1969, with computational resources smaller than a modern calculator, humanity built a machine capable of navigating precisely 384,400 kilometers of empty space, landing on another world, and returning safely. This was Apollo 11. This was the secret engineering that conquered the moon. And this was just the beginning.
So if we adjust the gimbal angle here...
That's then bias. That should compensate for the thrust vector misalignment.
Okay.
Copy that. Bringing her down slow. Left a bit.
Okay, so if we adjust the gimbal angle here, we should get more stability during stage separation.
That makes sense. It aligns with my calculations for thrust vector.
Alignment looks good from here. Keep it steady.
So if we adjust the trajectory here, we should gain an extra 7% efficiency on fuel.